Okay, I'll follow up on Tezier's presentation. I'm her colleague at ADASP. I'm supervised by Mathieu Fontaine, one of our collaborators, but I'm going to present the work I did on my master's. When I was still in Brazil, I worked with Professor Luis Biscaino. I worked with denoising of historical recordings, music recordings to be more precise. So just for a very, very quick background, all the recordings, old and new, have imperfections and defects. This is much more noticeable in older ones, obviously. So in the left, I have like a non-exhaustive list of possible degradations you can find on audio recordings. You can have clicks, thumps, hiss, rumble, and etc. There are different taxonomies and different ways to treat in traditional signal processing each one of these degradations. But what is interesting is that in some practical cases, such as 78 RPM recordings, you can actually have a composition of different artifacts. So you can have, for example, rumble and hiss and thumps and clicks, and this creates the old recording sound that's characteristic of 78 RPM recordings. I'll play an example just so that you can get the idea. Prepare your ears. This is a 1920 recording. Can I just do so far? No. Where is it now? Can you see now?
Because it's black.
Yeah, it's black. I can. If I hit just F and then I can do on tab. This should be. So yeah, you get the gist, I think. Okay, so I'll go back to the presentation. Actually, 78 RPM noise is, as I said, a composition of different kinds of noise, which makes it an interesting problem to treat. It's also very non-stationary, so it's a hard problem in traditional signal processing traditional signal processing standards. I tried to deal with this using diffusion models. I used the SDE formulation of diffusion models, not the DPM formulation. I'm not going to go very much into the detail of this because we saw this for the past day. But the point is, you can have a forward SDE that will take you from a data distribution all the way to the Gaussian distribution, and you can have a backward SDE, which is dependent on the score, which will do the reverse process and take you from the Gaussian all the way back to the data distribution. Diffusion models, even in this framework, can be trained with a standard regression loss. You can actually get the score if you train your model to estimate x at time 0. So I'll start with this background. Knowing this, you can do conditional sampling, as Eloy mentioned earlier and yesterday, and as Jean-Marie mentioned yesterday, by replacing the score with a conditional score. So you will have your conditional score, which would be, instead of gradient of the log of the probability density at time t, just the gradient of the log of the probability at time t given a degraded signal y. This can be rewritten using base in terms of a prior and a likelihood term. And the problem, if you're doing zero-shot conditional sampling, is how do you estimate this likelihood term so that you have a good reconstruction and that you can achieve your objectives. I'm using diffusion posterior sampling, which Eloy mentioned yesterday and which Jean-Marie also mentioned yesterday. So I use this model that is in this equation here for the likelihood term. This is particularly interesting because there is a scaling term, psi t, which is inversely proportional to the time. So as we get closer to diffusion time step 0, I'm increasing my conditioning, and so this ensures that I will have a consistent output. This is also interesting because psi prime is a constant term which I can regulate, and this is particularly useful for restoring audio recordings because you can control the strength of your conditioning through this psi prime term. Yesterday in Eloy's presentation and in Jean-Marie's presentation, we saw cases where for this diffusion posterior sampling term, you're using the gradient of your degraded signal minus a model degradation A applied to your clean signal estimate. So you're doing you're using this as your diffusion posterior sampling term, but in their presentation, the thing is A had to be a parametric model. So A was either an impulse-round response, and then you have the parameters for your impulse-round response, or a neural network. And in their works, you had to do some optimization procedure to find the best parameters for A. In my case, I did not want to make restrictive assumptions on A because I was working at first with 78 RPM denoising, and I really don't have a statistical model for that. So I simply made the hypothesis that A is additive. And my proposal was to use this A additive, so to take my clean signal estimate and to add a noise sample with a gain G to it, but to sample a different noise sample at each time step t. The idea is that I'm conditioning not to a single noise sample, but rather to an ensemble of noise samples which are similar to the one I want to remove. This can be very useful, for example, if you want to try to take noise examples from a recording which contains a track you want to restore. So you might do targeted inference sets instead of just using a single noise sample. Of course, there's a practical problem of finding out what would be the best value for G. If your inference set is power normalized, you can take an estimate of the power of the noise to estimate G. G will be the square root of your estimate of the power of the noise. I use the standard silence heuristic, so I calculate the power using a sliding window, and I take the minimal value considering this sliding windows to be the power of the noise, and the square root of that to be G. Of course, this has also limitations, but it's a bias estimator, for example. But it was a simple enough solution for me at the time. And about psi prime, in practice, psi prime should be tuned in a case-by-case basis. Because, for example, if you have very, very noise signals, then you want your conditioning to be less strong, to be weaker. Because in this way, you're not taking too much noise from your degraded conditioning signal. On the other hand, if you have clean signals, you want your conditioning to not be so strong so that you can retain most of the signal qualities without having restoration artifacts. I'm going to talk a bit more about this later on. In practice, for a large set of signals, not to have to listen to everyone and choose the best psi prime in each case, since I had pairs of clean and noise samples, it was synthetic example, I could use an SNR heuristic. This is likely suboptimal because psi prime is related to the power of the noise also, to the conditioning. But for the practical case of my experiments, this was enough. So in more details, talking about the experiments, I worked with classical piano music denoising. I used the CQT diff architecture, which was created by Eloy, the first version of it, so it's in the ICAS paper from 2023, where he also does inverse problem solving, but he doesn't work with denoising, he works only with bandwidth extension, declipping, and de-inversing, correcting saturations. In all cases, you have a parametric model for A. I trained it using Maestro, sampled at 44.1 kilohertz, and I conducted 3 experiments, 2 objective experiments, one for 78 RPM denoising and one for dehissing. The idea is using the same model on both experiments to show that you can have the zero-shot capability of removing noise that can be modeled additively with the diffusion model alone, without just changing the inference set. And for 78 RPM denoising, I also did subjective tests with actual old recordings from the 1920s to the late 1940s. For the baselines, I used the supervised deep learning models, so predictive models for denoising. The first one was also created by Eloy. It's a 2-stage UNet to remove 78 RPM noise. It is trained with pairs of clean data and noise samples which are joined together at different SNRs. And the baseline for the hissing with supervised deep learning was a model by Irigaray, which is the same model really, but just trained on a tape hiss dataset. And I also included the Wiener filter for the dehissing baseline because it's a standard method for dehissing, and it's in the audio restoration, music restoration literature for this. For a bit more of details, in the 78 RPM denoising and also in the dehissing objective test, I had 16 clean piano recordings and 16 noise samples. I paired them all together, and then I did this using 4 SNRs, 10, 20, 30, and 40 dB. So I had 64 signals in total. I used the SNR heuristic I mentioned earlier for choosing psi prime in the objective tests. And for my metric for quality, I used Visco audio. Visco is somewhat limited as a metric for audio restoration. Actually, there's no metric developed specifically for audio restoration. Visco was developed to assess the quality of compressed audio. So it can penalize certain defects more than others. For example, additive defects are typically very much penalized by compressed audio assessment algorithms, because you're not supposed to have that when compressing and then decompressing an audio excerpt. I put an asterisk there because I also put the FAD results. Although I'm not a big fan of FAD for the reasons we all talked about throughout this last weekend. These are my results. For the FAD, just as a side note, I used the clean set, the clean references as my FAD reference set. And so you can see that actually the results with conditional sampling were slightly worse. But they are competitive. They are in the same range. There's an overlap of confidence regions. Using the FAD, the FAD, I had slightly better results for diffusion. And with the hissing, with the same setup, I had very, very similar results. With the added note that diffusion conditional sampling did better than standard Wiener filtering. Now, what's interesting is actually the subjective test with the real historical recordings. For the subjective test, I actually had better results for the diffusion model. I tried 2 diffusion models. One is using a fixed psi prime value, which was one that worked okay-ish for all the 6 historical recordings. And the other one is really fine-tuning psi prime. And so for this one, I actually changed psi prime for each of the recordings and chose the one that I thought it was best for the experiment. And then this was evaluated by 13 volunteers. And then you can see there's a big difference in results. This is an interesting discussion. What we actually found out is that it's something that Jean-Marie talked about in his talk. The predictive models tend to remove noise completely, but at the cost of potentially muffling them and creating like low pass like artifacts. The diffusion model, on the other hand, did not remove noise completely. So I will show you an example which you can notice that there is residual noise on the background, but on the other hand, the signal is the content of the signal is better preserved. This is the example I showed you earlier. So I'll show you the baseline first, so you can get the idea of how it sounds. Oops. Maybe I need to be in presentation mode and then open all the windows and then. Oops. And then. Okay, this is good. This is the baseline for the same one you heard earlier. So you can actually notice the muffled sound, but there's zero noise. With the diffusion model, you have this result. So you can see it's more bright, but I think there is the residual noise. I can turn up the volume if you want, otherwise you can just believe me, this is better with headphones. So this was an interesting observation. And now I think we're short on time, so I'll just skip the other examples I had. What is interesting is that with this work, we managed to achieve denoising of historical recordings without an explicit parametric model for the noise. So this was cool. The empirical idea of using different noise sample at each diffusion time step, perhaps this could be used in other contexts. So it's something that could be useful. On the other hand, I wish I had tried to use this with larger pre-trained models on a wider range of experiments, not only with classical piano, but also with other instruments. Also, I had to use over 100 diffusion time steps for sampling. So inference speed was a big problem for me, and I did not use any of the techniques that Tesia showed. So this is something that can be obviously improved. And also finding an automatic way to determine a psi prime would be very, very interesting. But it's something that we did not figure out. And so this is it. I don't know if you have any questions or if it's okay for you.
Thank you, Bernardo. We have a question.
Yes.
Yeah, so for the... So I noticed that the step size, you use this normalization with the norm of the gradient.
I'm sorry.
DPS step size.
Yeah. With the norm of the gradient.
So
This is very expensive, both in terms of memory, because I have to keep the gradients in AutoGrad, and I did this. Everything I ran here was in a 2080 and a 3080 GPU, so I really didn't have a lot of memory. And yeah, so this is a huge overhead for both memory and time. Yeah.
But what I was thinking is that the normalization.
Yeah.
This is something that and I just came up with because I'm telling error, but there's no justification.
Okay.
So I was wondering if you try to get rid of this normalization and do something else.
No.
It's important.
I didn't actually. I really liked the fact that it controls the norm of the likelihood term.
Yeah.
And but I'm sure you could do better. Actually, the largest drawback of the work was actually fixing psi prime, because as I have a lot of inference time to get the samples, actually fine-tuning psi prime is a bit of a pain.
Yeah, it's a bit easier with normalization.
Yeah. But I think that maybe coming up with something different that was not dependent on a constant could have the advantage of fixing this problem exactly. But I didn't try this.
Yeah.
It's a good question. Yeah.
And the other question, so you have trained with some modern music and you added noise to that. So it's
Yeah, I trained with Maestro.
So there might be a mismatch between training data and what you see what you see at test time.
You mean for the diffusion model?
For example, if your text examples are band limited and the model hasn't seen band limited data.
Yeah. This is a big limitation too. The model will not be able to extend the band with this sampling. Yeah, you're right. I trained the diffusion model to unconditionally sample wideband signals. But in the 1920 recording, for example, I had severe band limitations. So of course, I won't. It's not the same case. So there could be a distribution mismatch.
Yeah.
But I also think that I'm not sure if that can actually help with keeping the high frequency content, because I did notice that the diffusion outputs were more bright, and I wondered if I had trained with band limited audio, would I get results that would preserve so well the signal brightness?
It depends on how you frame your task, right? If you only focus on denoising, if you apply the unlimiting in training, you will work better on denoising because there will be not so much distribution mismatch, but you will lose this brightness. Yeah, this is a good question. But if you don't want to change the brightness,
but this was not the focus. I was focused on denoising. Actually, we had an interesting discussion in the lab because there was another guy that was working with bandwidth extension, and he was trying to do exactly this, like extend the audio for band limited recordings. And the discussion was, should we get a very, very restrictive model and remove all noise, and then use bandwidth extension to try to fix the problems that we might have caused with a predictive model? Or should we do the opposite? Take a model that does bandwidth extension and possibly create very, very noisy recordings, because they will also extend the noise to the upper frequencies, and then apply the model, the predictive model, and hope that it will correct the errors of the previous one. You understand what I'm saying? Yeah. But I don't know if the guy that was working with me actually tried this or not, but it's also an interesting question. So, okay, I'll leave the floor to Mauricio.
No, I'll invite myself.